Good day, ladies and gentlemen. This is the second lecture of the third series of lectures introducing the RM software for filter design. In this lecture, we will discuss the introduction to the S domain. Here is the content of the lecture. First, we will give the rationale for the introduction of the complex variable. Then we will explain the Laplace transform. And finally, we will introduce the transfer function and the way of extraction of the properties of the filter via the transfer function. According to basic circuit theory, using the constitutive equations of the circuit elements and the Kirchhoff's laws, we create a set of differential equations governing the signals within the circuit. Since the solution of these differential equations is a function of time, we call the action as time domain analysis. Unfortunately, it is very difficult and even impossible to solve such systems of equation manually, even for a relatively simple linear circuits. That means we need an alternative way to analyze linear electrical and electronic circuits. In this lecture, we will introduce the Laplace transform as the powerful means to create a mathematical representation of the differential equations describing the circuit. In the place of differential, it will produce algebraic equations and will allow for creation of a function which encapsulates the properties of linear electrical and electronic circuits. That will be referred to as the transfer function. Given the transfer function, however, one needs means to extract the properties of the system to which it is associated. Hence, we will elaborate the procedure for time and frequency domain characterization of linear electronic systems, for which the transfer function was synthesized elsewhere. The unilateral or one-sided Laplace transform is defined by the following integral, where f of t is the function which should be transformed, and f of s is the transformed representative. In this expression, the lower limit is written as t equals 0 to power minus, because we wish to allow the signal, the function f of t, to include an impulse function at t equals 0. Or the other word, we want to encompass the boundary condition, the limiting point, which is t at equals 0, the starting point of the solution of a differential equation. It is assumed that the value of f of t is 0 for t less than 0 negative time. If the complex frequency is represented as S equals sigma plus j omega, where j is the imaginary unit, the value of sigma should be such as to ensure the integral to converge. The expression transposes a function given in the time domain, f of t, into a new form in the complex frequency domain. We use capital letters to denote that the voltage and currents are transformed. The opposite transformation, i.e. the inverse Laplace transform, may be expressed in the following way. Here C is a constant chosen so that to preserve convergence, and the final result, of course, does not depend on the value of C. Here are some Laplace transform pairs. So the first one is the delta function, which are unit pulse of 0 duration. Then located at t equals 0. Then we have the step function, which is expressed in two ways. This function has 0 value if the time is negative, and has a value 1 if the time is positive. Then we have a specific representative, which is related to a transfer function with a pole of nth order. On the left-hand side is the original, and on the right-hand side is the transfer function. And then at the end, we have this transfer function having two conjugate nth order poles. Here are some theorems which are valid for the Laplace transform. First is linearity, which means a linear combination of functions in time domain will produce the same linear combination of functions in the S domain. The derivative in the time domain is transformed into a transfer function multiplied by S, and the nth order derivative is transformed into transfer function multiplied by S to power n. The integral of a time domain function is transformed into the S domain by dividing the map with S. Then differentiation in the S domain, look to the right-hand side, is obtained by multiplying the time domain function by t to power n. And this is the next is the very important function, which is the convolution, meaning that integral, as shown here, of two functions will produce a product, integral of product of two functions which are shifted, will produce a product of two functions in the S domain. Then we have initial value, which means that the value of the time domain function at time 0 equals the value of the S-domain function multiplied by S at infinity, and the opposite, the value of the time domain function at infinity equals the S-domain function multiplied by S at the origin. Here is how the Laplace transform is implemented in circuit analysis. Here is the branch equation of a capacitor branch in the time domain. After implementation of the Laplace transform, we are getting the equation below, which is represented by a circuit on the right-hand side. One can see that we have the branch with capacitor denoted by SC, which is conductance, and a current source which represents the initial conditions. If there are no initial conditions, initial values, if there are no initial values in the time domain, there is no voltage on the capacitor at time t equals 0, then there will be no such source. When the complete system of equation is formulated in this way, then the current source values are coming to the right-hand side of the system of equations. Similarly, here is represented how the Laplace transform is implemented to the branch containing an inductor, and again we have a current source which is representing the zero valued current at the zero time in the inductor. Here is how the Laplace transform, inverse Laplace transform, is implemented when we have a function in the S domain. The simple pole is represented by the exponential function, and the double simple pole is represented by the same multiplied by t, and any higher order will have t to power of n. And here are at the bottom these complex pair of complex poles which are characteristic for circuit analysis for a transfer function which in fact has real coefficients which leads to complex conjugate poles, and this expression is very important for further implementation of time domain analysis of the transfer functions or analysis of the properties of the circuits in the time domain. So, some comments on selected theorems. Derivative of a function in the time domain maps into a function in the S domain multiplied by S. Integral of a function in the time domain maps into a function in the S domain divided by S. The value of a time domain function at the origin equals to the value of the S domain function multiplied by S at infinity. The value of a time domain function at infinity equals to the value of the S domain function multiplied by S at 0. Now we will say several words about the transfer function. It is a rational function of polynomials obtained by solving the circuit equation in the S domain, keeping all initial conditions equal to 0. Note that this solution comes in symbolic form, which means we are manipulating the complex frequency and the element symbols for the element values as symbols to produce an expression like the one which is presented here. And that is not an easy task. This transfer function is relating the output voltage and the input current. And so it is named transimpedance. The transfer function relating the output voltage and the input voltage is named voltage gain. The one which is relating the output current and the input current is named current gain. One should have in mind the orientation of the output current, which is frequently denoted with the opposite direction. And finally, if the output current and the input voltage are related in the transfer function, we are getting the transconductance of the filter. In the special case of passive LC filters, usually the voltage transfer function in use is a ratio of the output voltage and the source voltage, not the input voltage, multiplied by 2. Here, the output voltage is doubled to compensate for the loss of 6 dB. We saw what dBs are in the previous lecture, introduced at the filter's central frequency by the voltage divider RS, with the equality of RL and RS expected. In the next, to generalize, the transfer function will be denoted by H of S. Intuitively, the best way of representing a transfer function of a filter comes from the circuit analysis result, as depicted on the right-hand side, and it is referred the sum form. So the transfer function is represented as a ratio of polynomials expressed as sum of coefficients multiplied by s to power I. That will be, however, used very rarely, since, as we noticed, the Laplace transform works with poles, which of course is not the only reason for that. Instead, the factored form will be preferred. And now the transfer function is again represented as a ratio of polynomials, but the polynomials are represented in factored form. Here in the last expression, Zi and pi are the zeros and the poles of the transfer function respectively. A0 is used to define the gain or anything, transimpedance, transconductance, so at the central frequency of the filter. To preserve stability, to prevent the function to have infinite response at infinite frequency, the order of the numerator polynomial m and the order of the denominator polynomial n must satisfy the condition that n is larger or equal to m. N, the order of the denominator polynomial, is referred to as the order of the filter. Also, to preserve stability, the roots of the denominator polynomial, the poles of the filter, must be strictly on the left half of the complex frequency plane. That means their real parts must be negative. A transfer function is a minimum phase if all roots of the numerator polynomial, zeros of the filter, are found in the left half plane, including the imaginary axis. In the opposite, it is non-minimum phase. To represent the properties of the filter captured in its transfer function, we perform analysis of the transfer function for real frequencies at the omega axis of the complex S plane, and perform convolution to find the responses in the time domain for some specific, commonly accepted excitations. In that way, we produce amplitude and attenuation characteristic, phase characteristic, group delay characteristic in the frequency domain, and then in the time domain, pulse response, which is frequently referred to Dirac response, and step response, which is sometimes named Heaviside response. The amplitude characteristic is defined as the modulus of the transfer function computed at the imaginary axis of the complex frequency plane. Hence, it is a function of the angular frequency. It is an even function. By definition, it is obtained as product of the function of s and of minus s with s equals to j omega, which means h of minus s is a conjugate product of the function and the conjugate, and root of that is. Below, if the poles are denoted by alpha plus j beta and the zeros as gamma plus j delta, then for programmable form is obtained, which is represented on the right-hand side. In the specific case where the pole is real, then this reduces to a form where alpha is equal to 0 and nothing changes. While the amplitude is frequently, not always, represented in a logarithmic scale, the attenuation of the filter is, for historical reasons, generally used for expressing the modulus. Namely, the first filters were passive and one could only attenuate the signal by a filter. So the attenuation comes. It is defined as 20 logarithms of the reciprocal of the amplitude characteristic. The value is normally positive, and it will become negative if the amplitude characteristic becomes larger of unity. Here are two examples, in fact, two versions of the same function. On the left-hand side is represented the gain as function of frequency, and on the right-hand side is represented the same attenuation of the function of frequency. Being a complex quantity, the transfer function may be represented in a polar form as a product on the right-hand side above. Here phi represents the phase characteristic. In general, it is obtained as a natural logarithm of the ratio of the function and its conjugate at the omega axis divided by 1 over 2j. That is a formal definition. A practical definition, which must be used, here the key word is must, is represented here. The phase characteristic is obtained as a sum of Arcus-Tangens functions related to the numerator and the denominator, to the zeros and to the poles. So every zero and every pole has its own separate contribution to the phase. This is the only regular, only correct way to calculate the phase, but that is not enough. The evaluation of these expressions seems straightforward, but it's not. Namely, while implementing it, care must be taken for every addend to find the proper quadrant to which points the phase vector related to the corresponding pole or zero. The angles must be measured strictly counterclockwise. For example, on the right-hand side, we have a zero which is located in the left half of the complex frequency plane, Zi, top left. This means that gamma I is negative. When we want to calculate the phase at frequency omega, look to the imaginary axis, which is lower, below the imaginary part of the zero, delta I. So omega minus delta I is negative. Look down on the omega axis. The contribution to the overall phase angle will be, as you can see, 2 pi minus arctangens of the modulus of the ratio represented in the previous expression. This is a result. This is the characteristic, the phase characteristic of the very same filter, the amplitude and the attenuation characteristic was shown earlier. One is to note here the jumps in the phase characteristic due to the passing the frequency omega through the zero at the imaginary axis, and due to the changing of the orientation of the vector of difference s minus zi. So for low frequencies, it is oriented downwards. For higher frequencies above zi is oriented upwards, so it jumps. Now, since we saw the problems related to the expressing and calculating the phase, we instead use the group delay as a physical quantity expressing the time for which the envelope of the signal is delayed. So it is derivative of the phase with negative sign, so that the group delay is positive number. Here is the expression. One should note the negative sign of the derivative, which makes the group delay positive, and then that the numerators on the right-hand side are so written to preserve the sign of the real part of the zero or pore to avoid the use of signum function. So usually it would be minus gamma, but then we have no control of the sign. It is easy to recognize that zeros at the imaginary axis, look at delta equals to 0, or gamma equals to 0, sorry, gamma equals to 0, will not contribute to the group delay, since after the jump, as we saw in the previous diagram, the phase continues with uninterrupted value of its derivative. So the derivative is continuous. The function has a discontinuation. Now, since the group delay is derivative of the phase, the integral of the group delay should be equal to the phase, so that the area under the group delay curve is represented here as a difference between the phase at the origin and the phase at infinity. Now, due to the symmetry of the complex poles, phi of 0 may generally be 0, and that means that the area under the curve representing the group delay is equal to the value of the phase with change sign at infinity. For example, if all zeros are in at infinity, meaning the numerator polynomial is a constant, there are no finite zeros, m is 0, then we have a transfer function which is called polynomial filter, since only the denominator polynomial exists. In that case, the area under the group delay is n times pi half of pi, which is infinite value of arcus tangens at infinity. In the case when complex right half plane zeros are present, that is in non-minimum phase systems, one will have that the overall area will be obtained by this expression where the half of pi is multiplied by the sum m plus n. Here is the group delay of the filter we are following. One can notice the difference between the phase and the group delay characteristic. So the phase characteristic was a linear one, but one couldn't see that, in fact, this linearity is hiding a variation which could not be seen by naked eye. So we may say that the group delay characteristic is much more informative than the phase characteristic, and generally we will rely on the group delay when characterizing filters. Now we will go to the time domain. The analysis will rely on the convolution theorem, and we will repeat it here. So given two functions, f of t and g of t, and their respective Laplace transforms, f of s and g of s, then the Laplace transform of the product of the convolution f and g is simple product of the functions of the maps in the S domain. Having in mind that the products f of s and g of s may be easily obtained in the S domain separately, convolution may be used for performing effective inverse Laplace transform in order to find the time domain response to a given time domain excitation, such as this one here. To find this integral with the help of the tables given earlier, one needs to express the subintegral function in a form of partial fractions, and the expressions given below are valid for functions with simple poles only. So we see on the right hand side the summation goes over the poles of the excitation, which is g of s, and the poles of the transfer function, which is h of s. The values of the constant rj, which is referred to as a residue, are calculated according to the formula below, which means in a very simple manner. Here is one example. First, we have the transfer function of a second order so-called Butterworth filter to be discussed in the first, which was discussed in the first series of lectures. And then below we have the frequency domain or S domain representation of a or map of a sinusoidal signal of angular frequency of 1 radian per second and of amplitude of 1 volt. So the product is given below, and now we have to transform this expression into a partial fraction. Here are the values of the residues. This is to be elaborated further to make these expressions on the right-hand side a simple complex numbers. Now, the partial fraction expansion will look like this. The reader is expected to perform the inverse Laplace transform by himself based on the tables given earlier, while first calculating the numerical values of the residues given in the previous slide. Here is an example of Dirac and Heaviside responses to a Dirac and Heaviside excitations of the filter we were discussing earlier, not of the example. We will come back to the example during the examen. And as you can see, due to the linear phase or constant group delay, the Dirac pulse is almost ideally symmetrical with respect to his maximum value point, which is of importance in some application of filters in pulse transmission. So that would be all in this lecture. Thank you for your attention.